In this lecture, we're going to learn how to construct a PV versus P graph for an ideal gas and for a real gas as well. So the first thing that we'll do is I'll briefly go through the different aspects of what an ideal gas and a real gas is. Now, what are the differences between an ideal gas and a real gas? So quickly, an ideal gas is something that has it's a model for a gas, and it has two basic assumptions. One is that it has no intermolecular forces. So it has no intermolecular forces, or what you can say is that intermolecular forces are negligible. They are so small, they're so weak, that we can assume that they play no role whatsoever in the behavior of the gas. So that's the first assumption of an ideal gas. The second assumption of an ideal gas is that the particle size is negligible. Particle size is negligible compared to the volume occupied. So that's your second assumption. And what that means is that if you have a container and it has an ideal gas in it, so let's say I have a container, this rectangular container, and I have gas particles in it. So gas particles would be far apart. They will not be attracting each other. They would have very negligible intermolecular forces. There would hardly be any force of attraction between these particles. And the volume that is occupied, so the volume they are occupying, it's mostly these white spaces. So the volume occupied by the gas particles is going to be a lot larger compared to the volume of the particles. So the volume of the particles is very small. These particles are very tiny. They don't have any volume, but the volume in total they are occupying, it's very large. So the volume occupied is going to be the empty spaces plus the particles volume. And what the ideal gas assumes is that the particle volume is so negligible that we can simply ignore it, because the volume occupied is going to be probably equal to these empty spaces. So we can ignore the volume of the particles because it's going to be so small. The particles would hardly be occupying any volume. Most of the volume of the container would be these empty spaces. So the ideal gas assumes that particle size is negligible, or the volume of the particle is negligible compared to the volume occupied by the gas. We need to keep those two assumptions in mind, and we'll come back to those two assumptions. Let's first construct what a PV versus P graph is going to look like. Now we know that for an ideal gas, the product pressure into volume is equal to nRT. Now, if your number of moles and your temperature is constant, then this entire term would become constant. So for T equals constant, let's say we keep the temperature constant and we keep the number of moles constant. So if we keep them constant, and R is already a constant, then your pressure into volume, this product would also become a constant. It's going to become a constant. What that means is that we already know the relationship between pressure into volume. Pressure is inversely proportional to volume. What that means is that if you try to increase pressure of a gas, volume decreases. So if you increase pressure, then what that means is that you are decreasing volume. Vice versa, if you decrease volume, if you try to compress or squeeze something, if you decrease volume, you inadvertently increase pressure. So P and V are inversely proportional. but the product of pressure into volume is going to be a constant. So if pressure increases, volume decreases, but the product remains exactly the same. If volume increases, P decreases, the product P into V is still going to be a constant. So what the graph is going to look like, it's going to look like this. So we have two axes to the graph. One is where you plot the product pressure into volume, and then remember for an ideal gas that's going to be a constant, and on the other axis we take pressure. So for any pressure, let's say for a low pressure, volume would be larger, but the product would remain a constant. So the graph would be a straight line. It's going to give the same value. So it's going to give the same value, but this would only be true for an ideal gas. And remember the assumptions that I made. An ideal gas would have no intermolecular forces, and the particle size or the volume occupied by the particles would be negligible for an ideal gas. So it's going to be a constant straight line. So when the pressure is low, the volume would be high, so pressure into volume would be a constant. And when the pressure is high, the volume would be low, but the product pressure to volume would still be a constant. So it's going to be a straight constant line for an ideal gas. Now we'll move and discuss how this graph would deviate for a real gas. Now we'll see how this graph, where PV is a constant for all pressures, is going to deviate for a real gas. Now real gas, the first assumption for an ideal gas was that an ideal gas has no intermolecular forces, but a real gas has intermolecular forces. So a real gas has intermolecular forces. So that's the first deviation from our ideal gas behavior. So it has intermolecular forces. Particles would be attracting each other. Gas particles attract each other, although they attract each other weakly, but they do attract each other. So let's break our axis up, this pressure axis, into two parts. One is our low pressure part. So let's say this is where the pressure is low, and the other side is where the pressure is high. So I'm dividing the graph into two parts. One is the low pressure side, and the other one is the high pressure side. Now let's take a container which has gas particles in it. So here's my container. And it has all these gas particles in it. Let's draw this gas particle. This one is a red gas particle. Now what is pressure? Pressure is when these particles, they go and they hit the walls of the container and they exert a pressure. So for an ideal gas, these particles are not attracting each other, which means that this red particle is going to go and it's going to hit the walls of the container and it's going to exert a pressure. Let's call that pressure the ideal pressure, where particles are not attracting each other. So let's call that pressure the ideal pressure that a gas would exert, if the gas is an ideal gas. Now what happens in reality? In reality, what happens is that your gas is not ideal. What that means is when this particle is going to go and hit the wall of the container, these other particles, they would be attracting it. So this particle would be attracted by these other particles. The reason being because it's not an ideal gas. It's a real gas. Real gases have intermolecular forces. They attract each other. So as this particle is moving and going to hit the wall of the container, it's going to be slowed down. So in reality, in a real gas, gas particles would slow down when they hit the wall of the container due to intermolecular forces. When they hit the walls of the container and that is due to the intermolecular forces present. This particle would be pulled back by the other particles because those particles are attracting it. So in reality, the pressure that would be exerted, your real pressure for a real gas would actually come out to be less than the ideal gas pressure. Because in an ideal gas situation, the pressure exerted would be larger because there would be no slowdown. The other particles would not be attracting the particle that's going to hit the wall of the container. But in a real scenario, in a real gas, that particle would be slowed down. So your real pressure is going to be less than the ideal gas pressure. And if that is less, that means that the product which is going to be your real pressure into volume, the product P into V, would actually come out to be less than the ideal gas situation where, so it's going to come out to be less than, so your product is going to come out to be lesser. So P into V is going to be, it's going to be less than the P into V for an ideal gas situation. So if I plot this on the graph, what's going to happen is that there's going to be a slight dip because your product pressure into volume would be lesser. So the more the intermolecular forces, the more would be the deviation. So your graph is going to dip slightly and the product pressure into volume would decrease in a real situation. So this is for a real gas. The product pressure into volume is going to come out to be lesser. Now the second deviation, or the second part of the graph, the second error occurs at high pressures. So this error is due to high pressures. It happens when there are high pressures, and we're talking about a real gas right now. So, and it deals with the second assumption. So what happens at high pressures is, our second assumption was for an ideal gas was that particle size is negligible, or the volume occupied by the particles is negligible. Now for a real gas, the particle volume is not always negligible. Not always negligible. The way I can explain this is that if I have a container which is at low pressure, so I have a container and it's at low pressure, which means that the volume is going to be greater. So at low pressure, so this is a movable piston, and so this here is my movable piston, and they are gas particles. So the gas particles are at low pressure right now. So this is the low pressure situation. Now the volume occupied by the gas, the volume that is actually occupied by the gas, or the real volume, your real volume would be equal to the spaces, these white empty spaces in between. It's going to be equal to the spaces plus the volume of the particles. So your real volume is always going to be greater because ideal gas, what an ideal gas would do is that for an ideal gas we will assume that particle volume is negligible. So an ideal gas would only calculate the volume of the spaces, the empty spaces that is being occupied by the gas particles. So an ideal gas would only give you the volume of the spaces. It will not include the particles volume when you're measuring the volume. So your real volume is always going to be greater, but this error is going to be very less when you're talking about low pressure. Because low pressure, when you're at low pressure, particles are very far apart, and the spaces are a lot more compared to the particles. So for a real gas at low pressure, we can assume that particle size is negligible. But what happens at high pressure? When you have the same thing at high pressure, so when it is at high pressure, now at high pressure, particle size would no longer be negligible. Your volume, your actual volume, would be the volume of the spaces or the empty spaces plus the volume of the particles. Now the volume of the particles becomes more important because as you keep on compressing it, eventually there's going to come a time when there wouldn't be any spaces anymore. So at very high pressure, let's say I make another container. So there's going to come a time, here's another container. So there would eventually come a time when you compress the gas so much that there are no longer spaces in between. So you'll only have these particles and there will be very few spaces in between. So you keep on compressing the gas, and eventually there's going to come a time when there would hardly be any spaces, and your volume, your actual volume, would approximately be equal to the volume of the particles, because now the spaces are negligible. There are hardly any spaces in between. So as you keep on compressing a gas, because an ideal gas assumes that particles have no volume, but this error becomes more dominant at high pressures. When at high pressure, your actual volume would be equal to the volume of the particles. Now what an ideal gas in this situation, because it assumes that the particles have no volume, it would give you zero volume. So the difference in volume would be much greater at high pressure than at low pressure, and your real volume would come out to be larger. So when you calculate the product at high pressure into volume, because there's going to be into volume, and if you take the real volume, this would come out to be larger compared to pressure into volume for an ideal gas. So if I plot a graph, as you keep on increasing pressure, your real volume keeps on increasing. So if I plot this on the graph, it's going to look like this, because pressure into volume, the product would keep on increasing at high pressure. So because your real volume keeps on increasing, and it's going to look something like this. Now the last part, this is the graph for an ideal equation, PV versus P graph. It's supposed to be a straight line, and for a non-ideal or a real gas, it's going to deviate from the ideal gas behavior. So there's going to be a dip initially. So there's going to be a dip initially. It's going to decrease. P into V product would decrease, and then it's going to rise at higher pressures. And I've already explained what are the reasons behind that. And as the gas becomes more and more non-ideal, this behavior becomes more dominant. The dip would increase and the rise would also increase. Now, under what circumstances, how would you know that a gas is behaving non-ideally? So how would you determine whether the gas is close to ideal gas behavior or it's behaving non-ideally? The number one thing is if it has a lot of intermolecular forces. So if the gas has high intermolecular forces, then that would mean that it's going to behave non-ideally. It's going to behave non-ideally because an ideal gas assumes that it has no intermolecular forces. So if I have three gases, let's say I have two gases. One is ammonia and the other one is hydrogen. Now, ammonia has hydrogen bonding. Ammonia particles in ammonia will attract each other very, very strongly, whereas hydrogen has very weak van der Waals. So hydrogen is only going to deviate very, very slightly. So if I draw the graph for hydrogen, there's going to be a very slight deviation from ideal gas behavior. So it's going to be something like this. So there's going to be a very slight deviation. Whereas ammonia is going to be, on the other hand, ammonia is going to be very non-ideal. So this graph would probably be of ammonia. Ammonia is going to deviate a lot because ammonia has hydrogen bonding, it has very high intermolecular forces, so its behavior is going to deviate a lot from ideal gas behavior. Now, the second condition in which a gas would behave very, very non-ideally is low temperature. So when a gas is at low temperature, then the gas would behave very ideally. It's going to have a very non-ideal behavior. The reason being that at low temperatures, particle would have very less kinetic energy. So particles of gas are not energetic enough. They're not energetic and are not able to overcome intermolecular forces and are not able to overcome intermolecular forces, which would mean that at low temperatures, whenever a gas is at low temperature, it's going to behave very, very non-ideally because intermolecular forces become more dominant. So at low temperature, intermolecular forces become more dominant and the deviation from ideal gas behavior increases. So intermolecular forces become more dominant. So either the gas has a lot of intermolecular forces or it's at very low temperature and the intermolecular forces become more dominant, that the gas would start behaving non-ideally. So another way to draw the same graph is, I'm going to draw another graph and let's draw this graph again. So another way to describe this is, so let's have another graph. So this here is pressure and this over here is pressure into volume. And this is for an ideal gas. Now at very high temperatures, all gases would behave ideally because they're very energetic and they're easily able to overcome intermolecular forces. So intermolecular forces are negligible at high temperatures. So intermolecular forces are negligible at high temperatures because particles are very energetic. So intermolecular forces are negligible at high temperatures, but at low temperatures, intermolecular forces become dominant. So intermolecular forces become dominant at low temperatures. Become more dominant at low temperatures. So if I have a graph and I have this is a graph for a real gas, for an ideal gas, and let's say I have a graph for an ideal gas. Now at very high temperature, the gas would behave very ideally because it can easily overcome intermolecular forces. So the graph would be something like this. It's its shape would be very similar to an ideal gas. So at high temperatures, the gas would behave very ideally. But at low temperatures, intermolecular forces become more dominant, and when they become more dominant, the gas would start behaving non-ideally, and the graph would look something like this. So at low temperatures, the behavior would become more non-ideal. So this would be close to a non-ideal behavior. So at low temperatures, intermolecular forces become more dominant, and the shape of the graph would start to deviate.